Let's solve one more problem on type 2 partial fractions for repeated linear factors. Sorry. So we have this example 2. In the last video, we did one more example. So let's take this one. Okay. So what is the example we have? We have 3x plus 2, the whole divided by x plus 1 and x square minus 1. So let's see. Since we already know that this is a type 2 repeated linear factors, let's assume for a minute that we did not know this and you are solving an exam problem, and the first step for you to identify is what type this problem belongs to, whether it's type 1, type 2, type 3 or type 4. And since we're talking about only proper fractions where the degree of numerator is going to be less than the denominator, we know that it's going to be one of the first three types and not improper fractions, which is type 1, type 2 and type 3, which are proper fractions. So the first and foremost step after checking whether it's a proper fraction or not, the first and foremost check that we need to do is whether the denominator or any terms or any factors in the denominator can be factorized and simplified further. Let's check that. So this one over here is linear by itself, and this is the most simplistic way to express. Hence, we cannot do anything more than this for now. And let's focus on this term. This appears to be quadratic. In a way, it is quadratic, not appears to be. It is quadratic. But let's say whether we can simplify this quadratic equation into linear factors. Let's check that out. And since on the face of that we can see it's x square minus 1, it sounds more like a square minus b square. We can use that identity which expands into a plus b and a minus b. We can apply the same logic over here, and that way we can expand this as follows: x square minus 1 is equal to x plus 1 and x minus 1. And then we can substitute that equation or those linear factors which we have moved from quadratic. So if you see here, what we have done in essence is we have converted the quadratic equation into linear factors, which is what we wanted to do it to simplify the expression. And now once we put this back into this equation, let's see what we get. If you see here, the whole thing is written as 3x by 2. So this part over here is this part. So this one quadratic has been substituted by two linear factors. And now after you do that, what do you see? You see this x plus 1 here from the original equation, this one, and one of the factors x plus 1 from this equation. They both are same and they both are repetitive. So we can write them as follows here: x plus 1 the whole square, and then this leftover term of x minus 1. So once we come to this point, what we can do is we can call this as type 2 repeating factors, because all are linear in nature. If you see, all are linear and one of the terms is repeating. So it's become type 2 repeating. And that's how you identify that type in the first place. And now once you identified, the biggest thing in partial fraction is the opening step, which is this step. If you get this right, like I've told, you get 90% of things right. Okay, and you are already 90% there because the rest 10% is just solving, or maybe 95%. So what do we do now? We know it's type 2. So as we discussed in the previous two episodes, just count the number of factors in the denominator after factorization. Once you factorize and separate out all the linear factors, just count the number of terms. If you see here, if I separate this out, this is term 1, this is term 2, T2, this is T1, and this is T3. So whatever are the number of linear factors in the denominator, these are not terms, sorry, these are factors. I'm sorry, I'm just using the word interchangeably. Excuse me for that. Okay, these are factors. So linear factor 1, linear factor 2, and linear factor 3. So whatever are the number of linear factors in the denominator post factorization, you just exactly take that many constants. Okay, and that's what we have done here. If you see, the first factor has the same denominator. Where is this? Okay, over here. Okay, if you have that, you take the linear factor. Once you put this way, you have the linear factor x minus 1. That's what you have. And for the repeated factors, you need to have three constants. So we have constant 1, 2, and 3. The first one is simple linear, so it goes as it is. The second and the third factors, or terms in this case, because it's separated by the plus sign, here it becomes the terms. We have x plus 1 the whole square, so we separate that out. We are sure that this is the easy piece. We have the last term where we take the whole denominator factor, the repetitive factor, as it is, and we put that. And this middle term, like we saw, we would not know upfront whether this will exist or not. So hence we assume that this might exist. And the way we do is we just reduce the degree of this degree of the repeating factor by 1, and we put this. So this also gets linear. And that's how you make these 3 factors. And that's the most important question. And why do we do that? Like I told you, some linear fraction, let's say if this was a linear fraction, a partial fraction given to us over here, ABC over here, this was given to us. Okay. So if this was given to us, we would not know, in some cases this will exist and you will still get the same denominator, this one, x plus 1 the whole square. In some cases this will not exist and you still get the same denominator. So we would not know whether this term was there to begin with or not, and that's the reason we assume that, because the LCM will give you the same denominator, so we cannot just go based on that. So we assume that. That's kind of a short explanation of why we do that. And like we said, we assume all these terms to be constant and just we put this positive sign. And once you get this, like I said, you're 90% there already, and you can just rest is easy. In this episode, apart from the substitution, I wanted to emphasize there are 2 ways to solve this. We have been seeing one way, which I call method of substitution. I'll quickly zip through that, but I want to also introduce you to the second concept of how can we solve and find the values of these constants. Our objective is to find the values of this constant. That's our objective. Okay. So let's get started. So what do? We take this whole equation and we substitute with this. So we have got this way where we have we multiply, cross multiply and take the common LCM to make sure the denominator matches with this on both the cases. That's what we have done here. If you see, the denominator matches here. Exactly. What did I miss here? Yeah, the denominator matches here exactly. And what we do is we cross multiply. So once we cancel the denominator, if you see, this denominator I've kept in this format, and over here I've taken in this format. So it's the same thing, so you don't have to get confused. Okay. So once the denominator gets cancelled, all we have left is with the numerator. If you see, with 3 constants A, B and C on the right hand side. And the way we do is, the first method, like I said, we'll do substitution of different values of x and find 1 or 2 constants at a time. And the way we do is, okay, first we can take this equation as it is. So let's say we take x is equal to 1. What will happen if we take x is equal to 1? If we take x is equal to 1, over here, 1 minus 1, over here and here, 1 minus 1 is equal to 0 and 1 minus 1 is equal to 0. So B and C will get, we'll eliminate B and C, and all we have left is A, and we can find the value of A. And that's what we have found here. So we have taken x is equal to 1. We have eliminated B and C, and we have got the value of A. Then we see we can make any other constant 0. And if you see here, if you assume x is equal to -1, let's see what happens. If you assume x is equal to -1, then over here, this will become -1 plus 1, and this will become 0. So that way we eliminate A completely, and then what we will get? We eliminate A, and we eliminate B also, because B also over here, x minus 1 square plus minus 1, it will become 1 minus 1. So we eliminate B also. So we get the value of C. And now since we have the value of A and value of A and C, you can substitute any value, any small value, and you can plug in the values of x, you can plug in the value of A and C to get the value of B. And the value of B is minus 5 by 4. So that way we have got the values of A, we have got the values of B and C, and our objective is to go and put back in this equation. That's how we complete the partial fractions. We have to replace these values, or we have to remove these constants and put back the values of A, B and C, and that's how the final closing step will be, and we'll see that over here. Okay, so I've taken I've removed A, B, C and put the values of the newly find actual values of A, B and C. That's how we conclude. And that's an easy piece. That's concludes the partial fractions. I want to introduce you to second concept of equating the coefficients. It's another way. The first method is called substitution method. If you see here, substitution method. There's another method called as equating the coefficients, and we can use any method. But why I want to introduce this method is sometimes it's not possible to use method 1 to find the values. In such cases, you can use this. At a high level, you can use both the methods to find either way. But if you're comfortable with the first method, that's okay. You can try doing that. But for some reason, if you're not able to get the value, sometimes you may not get the value because there will not be any single value which will knock off or eliminate the constants a, b, c. Then you can use method to equating coefficients, or whenever you have higher degrees of the polynomials, cubic and more than cubic or quadratic and long polynomials, you can use this method. So let's spend a couple of minutes in understanding what this method is all about. So we take the first step as it is, where we cancel the denominator. If you cancel this denominator and we just match the numerator on the left and the right hand side, from that step we come here. So that's until that point everything is constant. So we are matching the numerators here on the LHS and right hand side RHS. Okay, and then what we do is, since we know that we have terms of x square and we have terms of just x to the power 1 and constant, but the right side does not have all the coefficients. So what we do is we completely open up the brackets over here and we just bring in the terms together. For example, once I multiply this inside, I'll get this one, the first three terms, ax square, a into 2x, then a into a. So I open up all the brackets, and then what I do is I group all the terms with the degrees of x same together in terms of the descending order. For example, if you see my underline, I've got two underlines on the red. That means there is x square here and there is a x square here over here, a and b. So I bring those two together. So it becomes a plus b, and x square is common. I bring that way. Then we have some terms which has coefficients of x. So we have 2ax in green and we have cx in green over here and over here. I can bring those because those are common terms, variables in x of degree 1, right? So I'm bringing that together, and then I bundle up all the constants together, which is in underlined with three colors, a, b and c, and make sure that you take those negative signs. So a minus b minus c, I've taken that, and right hand side remains as it is, so no change. And after I do that, what I do is I try to match each term on the left side with the right side. For example, okay, right in the left side we have a coefficient, that's why it's called as equating coefficients. So let's match the coefficients of x square on the left hand side with the right hand side. In this case, the right hand side does not have any x square term, so we can assume that the coefficient of x square is 0. So we can say that a plus b, the coefficient of x square and x square match. So the coefficient of x square is a plus b and the coefficient of x square is 0. So we just say a plus b is equal to 0. We just match the coefficients because that has to be true, because we have to match apples to apples. Similarly, the coefficient of x, variable x, which is x to the degree 1, is 2a plus c over here. On the right hand side, the variable of x to the degree 1 is 3. So we match that in the second equation, 2a plus c is equal to 3. We match the coefficient. And last not but the least, the last term is kind of only the constants, or you can think of this up as x to the power of 0 in terms of polynomial. So we have all constants. Similarly, on the right hand side, we have 2 as a constant. We can think about 2 as 2 into x to the power 0. So you can assume that the coefficients of x to the power 0 we are matching, which will be a minus b minus c is equal to 2, and that's what we put here. So now what do we have here? We have got 3 equations and 3 unknowns, and that we can solve anyhow because we can add, subtract, we can pick up easy equations, and then we can solve it that way very easily. That's another way of solving that. In this case, if you see, so what I'm doing is equation 3. So in the first 2 equations, I just have a plus b and a plus c. So using these 2 equations, I can remove the value of, I can express b in terms of a using this equation, and over here I can express c in terms of a, and then I can take those 2 values and put in equation 3. So I'll keep the a as it is. We're trying to find the a. This b will be this b over here. B is equal to minus a. That's what I put here. And over c here will be 3 minus 2a, which is what I put here. So now this equation becomes only one equation and one unknown. Okay, and then we can find the value of a. A is equal to 5 by 4. It will give the same answer. Similarly, you can find out b and c by picking up the right equations I put here, and then you can get those values. So, and the answer will be finally same because we have to put back the whole equation and substitute those values, or remove this a, b, c and put those back values. That's how we conclude the partial fraction. And like I said, most of the problems can be solved by either of these methods, or all the problems can be solved by either of these methods. But in some cases, for the most of it, method 1 may not be possible because of the number of factors involved or the degree is high and so on and so forth. In those cases, we can use this method too, called as equating coefficients. And that's how we summarize it. I'll see you in the next episode.